Um, let's talk about the stuff that we finished up with on Friday. Okay. We started with 2x squared minus 12x plus 13. Okay. Our goal was to take that. We were calling that standard form. Okay, or polynomial form, and then transfer that into vertex form. And the overall goal of that is to eventually develop a skill to where we can quickly graph these things. Okay, so as we kind of try to develop that skill, there will be obviously in your homework questions that they structure that kind of reverse engineer that process. So maybe they start you with the picture and ask you from the picture, can you pull things out of that and generate vertex form? Okay, so they're trying to get you to look at these things from different perspectives to see if you have the ability overall to change into vertex form. Okay, so what I want you to understand is that the overall process, the overall skill is to be able to take any quadratic and put it in vertex form. Okay, some of the questions though in your homework might seem that your overall goal is kind of the reverse of that. Okay, their idea is if you can do it in reverse, then you can probably do it forward. Does that make sense? And you've seen that a lot, maybe already in other courses. If I can factor, their argument is you can probably FOIL, or if you can FOIL, you can probably factor. Okay, so you would see those kinds of problems together. Do one, you do the other. Yes.
Oh, we take a quiz of this. Are we allowed to use like that?
Well, I'll let you use, so GeoGebra, I'm probably on a quiz on this, I'm probably going to say no to GeoGebra. I'll say yes to Desmos. The reason I say no to GeoGebra is because GeoGebra, when I type it in and I right-click on the function, it actually allows me to put it into vertex form. It'll do the work for me.
Actually?
Yeah, so GeoGebra has a computer algebra solving system, okay, which is like a you guys have TI-83s, right?
No.
A TI-89, if you get into like engineering or something like that in college, taking some high-level math classes, you'll buy a TI-89. And basically TI-89, what that does for you, the difference in between it and TI-83 is that it will solve the equation for you, okay? Because at that point, if I'm in engineering courses, I'm in Calc 2, Calc 3, Calc 4, that kind of stuff. The assumption is I know how to solve quadratic equations. I know how to solve linear equations. So let's use a device that's going to allow us to get to that amount or that value a lot quicker than having to sit down and do all the intermediate algebra. Okay. So that being said, GeoGebra has that kind of built into it. Kind of show you what I mean by that. And it doesn't always. It just depends on the function, the way you type in, that kind of stuff. But there are situations where it will definitely do most of the work for you. So let's see if I type in, let's just go 3. I don't know if it'll do it for this one, but let's write that in. So I right-click on it, so see here, it doesn't allow me to do it on this one, but there are, maybe I do it this way. Let's go like y equal, or let's go, I'm going to write this. All right, so I just wrote a line in, okay, just to show it with a line. It will do it occasionally with higher power polynomials, but I typed in a line, and if you saw me type it in, I typed it in like slope-intercept form. You see how when I right-click on it, it gives me these options. I can put it in standard form. I can put it in what we call parametric form. I can put it in that form, which is kind of a version of standard form. Or I can put it in what we are most familiar with and what we like and prefer is y equals mx plus b, slope-intercept form. Slope-intercept form. Okay. There are times where it will do that for other functions, other types of functions. That make sense? Okay. I haven't messed around with, and I don't get into the manual too much with GeoGebra on, why maybe it's not allowing me to do it to that one, but some other ones it will. So that's kind of why I would avoid that on a test or something like that. Okay, so going back to 2x squared minus 12x plus 13 from Friday, it asks us to get the vertex form. And the approach that we want to take with that initially is to kind of work through the completing a square process. So we completed a square, we took half of this 12, got 6 squared that, we divided everything by 2 first, so that 12 actually turned into a 6. So we're looking at this line right here, after we divided everything by 2. We took half of this 6, squared it, got this 9, added that to the right, and then we added to the left. We had to add it as 18 halves, so we had a common denominator over here. They gave us this line here. Remember, the purpose of completing a square is to generate a right-hand side that became a perfect trinomial. So we're going to rewrite it as x minus 3 squared. And here's the idea. This right here is the main goal, to be able to generate that. Because if I understand what it means for us with transformation, I know I got a parent function of x squared, which usually has a 0, 0 as a vertex, right? That is saying now you're going to take that 0, 0 and you're going to move to the right 3 units. So now you know the x-coordinate of the vertex of 2x squared minus 12x plus 13. It's 3 units to the right of where it was for the parent function. Okay? Once we go through and solve for f of x, then it gets down to this here. Okay, so again, that minus 3 shows up, and that's where we move to the right 3 units from 0, 0. And this minus 5 then says, well, you're going to move down 5 units. Okay, so that 3 and that negative 5 tell me my vertex, and that's what we talked about on Friday. You guys remember saying that, doing that? Okay. At that stage, then we were interested. We knew this thing was concave up because that 2, okay, our multiplier out front, our vertical stretch is a positive number. That means it's going to be concave up. So that means if my vertex is in the 4th quadrant and it's concave up, that means my curve has to cross the x-axis, meaning I have x-intercepts. Okay? So if we have x-intercepts, the idea is this becomes 0, f of x becomes 0, your y value becomes 0, and you solve that equation right there. Okay? Once you've completed the square and you get down to this equation, it's always going to be add an amount to both sides, divide both sides by something, square root both sides. Add, divide, square root. It might be subtract, divide, square root. Okay? And that will get you your x-intercepts every single time, instead of coming back up to the original thing, okay, how do I use factoring or AC method, all that kind of stuff. You've already done most of the work here. Just keep going with it. Okay? So it gives us the x-intercepts here. Some things we talked about once we graphed it. So we got our x-intercepts, we got our vertex. Remember last year in algebra, you talked about that line. Now, my graph's going to stink, but that line is called the what for a parabola? And every parabola has one. Line of symmetry. It's called the axis of symmetry for a parabola. It goes through the vertex, right? The vertex had a coordinate of 3 for the x-coordinate, right? So that line, that blue line, is x equals 3. Now, what is nice about that, and nice about every parabola, this is why we call it the axes of symmetry, is that if I find a point over on the right-hand side, that point right there, okay? When I find, if you go back to geometry, and this is the reason we talk about this stuff in geometry, if I was just looking at that blue line, so let's say this is the blue line, and I say that this is that point on that curve that I just pulled off, okay? How do I find the distance to that line right there? What kind of line do I use? You find the distance from, if I'm standing right here and I want to walk to that line, how do I do that? Well, okay, horizontal because that line is vertical, right? So give me a better phrase than that. I would agree with it.
What did you ask?
How do I go from so what if this is my line? Do I go from that point horizontal to there? Because if I did, that'd give me maybe that distance there, right? Is that the distance to that line? Or is that the distance to that line? Because remember, if you're not on the line, how do you go from a point to the line? If I ask you from your seat, walk to the board. Walk to the whiteboard. Or actually, let's walk to the wall that the whiteboard is on, or the smart board is on. Okay? And I ask you, what is the distance from your seat? How are you going to do that?
You gonna go to the corner? From where you are to the corner? You go there from where you are to the filing cabinet? What's the distance from you to the wall? Because there is one distance that we talk about. P. Perpendicular. Okay? Because that is the shortest distance. Does that make sense? Lots of distance, lots of different routes you can take from that point to that line. But there's one and only one that's the shortest, and it's perpendicular. So up here, the idea about this line of symmetry is that that distance right there, whatever that is, ends up being the same as that distance right there. Okay? And it's going to find me that point right there. Does that make sense to everybody? Okay? Well, what's nice about that is that's true for every single point. Well, don't we know that point right there is the x-intercept? That one is also an x-intercept. Okay? So what we know then is that that distance right there between the axis of symmetry and that x-intercept to the right is the same as that distance right there from the axis of symmetry to the x-intercept on the left. Okay? And having that information, and what we're going to need on every single problem, maybe, maybe not. Okay? But having that understanding will allow you at times to say, okay, well, if I, maybe for some reason, I'm only able to find maybe my two x-intercepts, and I'm struggling with my vertex. Well, my vertex is halfway in between those two x-intercepts, then, right? Or maybe I'm struggling with finding one of my x-intercepts. Okay, maybe they give me one, and they give me my vertex. Okay, and I need to find the other x-intercept. Well, I hope I don't go through all that work again. I hope I use the relationship. Well, if I know one x-intercept is 4.58, I know my vertex is located at 3. And if I subtract those, it gives me the positioning to get, or the distance to get my my other x-intercept. Does that make sense to everybody? Okay, so understand that relationship between that yellow distance and that green distance is important for us. Then we talk about the range and the domain of these things, which will be something they continually ask kind of all the time. Okay? I think at the end of the period, we kind of started, so it wasn't this one specifically, but I started to talk about, okay, well, let's see if we can gain the same information. Let's see if I can take that parabola right there, and I'm giving you the function as negative 3x squared minus 24x minus 46, and I ask you, can we put this in vertex form? Okay? Well, because you know both, you know the graph and you know the equation right now, the formula in polynomial form, you got some options. Maybe you want to just kind of plug away at g of x like we just did, complete the square root of that thing, which we will do to get that practice. I want to approach it a different way, because this should be maybe a little bit quicker. Okay? Do you know what your vertex is from this picture? What's your vertex? Okay. Negative 4, 2 is my vertex. Doesn't every parabola, no matter what it is, follow the form of a x minus h squared plus k? Yeah. Isn't this h comma k? Yeah. So doesn't that mean f of x is equal to a x minus the negative 4 plus your k? Doesn't it mean that? Okay, now think about that. Think about what we know about transformation. Does that plus 4 take the parent function x squared, whose vertex is at 0, 0, does it move it left 4 units? Yeah. Does that plus 2 move it up 2 units? Yeah. Awesome. And if that's all I did to x squared, my parabola would look tablet died. My parabola would look like that, right? Concave up. Mine's concave down. So in the back of my mind, because we understand transformations from chapter 2, in the back of my mind, I know that my A coefficient has to be what kind of number here? Negative. Has to be negative. Okay? Has to be negative. Now here's the thing. If it's negative, thinking back to just some key points, on your parent function. Would you agree those are key points in your parent function? Okay. Well, if this was so if I just made this a negative x plus 4 squared plus 2, then doesn't that just take these points and flip them once I move over here? Yeah. Okay. Well, then doesn't that mean that I should be able to go from that point down 1 over 1, and there should be a point right there on my curve? That point right there, modeling that one, or corresponding to that one, does that make sense? Okay, well, does that point show up on this blue or purple curve here? No. So it's not just a negative A. Okay, it's not just, there's a coefficient here that we've got to kind of worry about. Okay, and it would be nice if we knew another point on this graph. Let me start this over real quick. It'd be really nice if we knew another point on that graph. Okay, other points that we're looking for that are convenient would be x-intercepts and y-intercepts. Okay. Now, when we look at that graph, I don't have any y-intercepts that I can see, right? They're there, but they're way down there. Okay. I got some x-intercepts. Now, here's my thought. Do I really know what those x-intercepts are?
Nope.
No, they're somewhere between -3 and -4 and -5 and -4, but I'd have to kind of guess, right?
Yep.
Okay, so x-intercepts aren't going to work. But all I'm looking for is a point. I like x-intercepts and y-intercepts because they have coordinates that incorporate zeros, right? So it would allow when I substitute to get either that to go to 0 or that to go to 0 or whatever. But are we pretty certain that that point right there is -3, -1? Or maybe that point right there, because of symmetry, -5, -1. Okay, well, think about this. That's an x value, and that's y, I'm going to write as f of x. Can I plug that stuff in down here to solve for a? All right, so let's plug in f of x being -1. Got my a. Now my x is -3. Does that give me an equation just with a in it then? So we get -1. Okay, -3 plus 4 is 1, squared is 1, times a is just 1a, plus my 2 then. What's a got to be? A is -3. Okay, so now I'm going to come back up here, and we'll plug that a in. So f of x is equal to -3, x plus 4 squared plus 2. And that's a way to generate from just a graph the polynomial that it's attached to. Okay, now that automatically puts it in vertex form for us, right? If I FOIL that out, if I went x plus 4 squared, give me x squared plus 8x plus 16, multiply by -3, through that, add 2, it should end up giving me this thing there. Okay? Now, that thing there, what's the y-intercept? -46. Okay? And really, from that, that's all I can gain right now. I know it's a -46, and I know that a is negative, so it's concave down. So from that, I don't know what a vertex is. I don't know all that kind of stuff. So I would have to do a little bit of work to get there. Okay? But
Is the a that you're anyway going to always be the a that you like started with? Like, I never problem with telling you.
yeah. So like knowing this here, is that what you're saying?
Yeah.
Yes. But if you don't know this, if that was not on here and this is all you had, that's the approach you. Because I'm thinking you're thinking, well, I don't need to go through this if I have this, right? And I totally agree with that. Okay. If you have this and you have the graph, my thought is pick the vertex off the graph, and you got x plus 4 squared plus 2, right? And then you look at that polynomial form of -3x squared minus 24x minus 46. And you say, well, I need that -3 to be my a, and I've got my formula. Is that right? That's perfectly fine. That works. But that's when you have both those components. Okay. Let's just for practice. Let's see if we can complete the square with this thing and generate the same exact results. Okay. So if I'm completing the square, we said the first thing to do is nope.
Can we take out -3?
We want to take a -3 out. We divide everything by -3, and I also want to move this 46 to the other side. Okay. So we talked about dividing everything by A and moving C to the other side of the equation. So when I do that, it'll be g of x, d of x, we'll divide it by negative 3. Okay, I'm going to add that 46 to both sides and divide that by negative 3 so it becomes minus 46 thirds. Does that make sense? Okay. And that will then leave me with x squared plus 8x. So we can just divide everything by 3. I always divide by it, and negative 3 in this case. Always want to divide by A and add C. And those two steps are independent of one another, or you can do them together. Doesn't matter. We kind of do them together here. Okay, next thing, you take half of that, square it, add to both sides. So add 16 to that side. Now, just so that I have common denominator of 3, I'm going to add 48 thirds to this side. Okay? Okay. What's 48 thirds minus 46 thirds? 2 thirds. So I'm going to rewrite this as the opposite of g of x over 3. Can I take that negative right there and put it up in the numerator? Okay. And then plus 2 thirds equals. Now the reason we did all this was so that thing could be rewritten as x plus that b over 2 term. 8 divided by 2 is 4, so it'll go plus 4 squared. What can I do to get rid of all those fractions? Multiply everything by 3. So I get negative g of x plus 2 equals 3 times x plus 4 squared, right? How do I isolate g of x? Subtract 2. How do I get this to be a positive g of x? Multiply or divide by a negative, right? So it gives me a negative 3, x plus 4 squared. Multiply this by a negative, positive 2. Is that the same thing as what we did there with the graph? Yeah. Okay. Is that okay with everybody? There's one other thing that you know. Okay, but you kind of learn these things. I'm going to argue, you've already did the completing the square process before. You targeted the vertex formula before in Algebra 2. Okay, you've targeted, we've done it already this year, and you did it in Algebra 2, something that we're going to talk about here in a moment. But my hope is that you start to integrate all these things together and realize they're all the same thing, even though you learn them as kind of individual concepts in Algebra 2, and you learn how to do them. Now my hope is, yeah, I learned that maybe within a 3-week span and said it was 3 different things, but now within 2 days, hopefully we see that those 3 things were all actually the same. Okay? So completing the square, this vertex form stuff, and what I'm going to show you here are identical. You guys remember, like if I gave you a parabola and asked you what is the maximum or minimum, where does that occur? You would say x first is equal to opposite of b over 2a. You remember that little formula?
Yeah.
Okay. That is the vertex. I should write the x coordinate of the vertex. Okay. So here's where that thing comes from. Think about this. Okay. We did this with the projectile questions, the rockets that were launched, all that kind of stuff. So let's talk about why it works. Okay? And now that we understand transformations a little bit better, maybe this makes a little bit more sense. I'm going to say f of x starts off as just some arbitrary ax squared plus bx plus c. I don't care what it looks like. I don't care what a, b, and c are, because this should work no matter what they are. Okay, and this little proof here We'll confirm that. We just complete the square. So we say completing the square, we want to subtract C from both sides and divide everything by A. So we'll do that. Come over here and do that. Yes. 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 Okay. So when we solved, we did this with the quadratic formula because this is gonna be a little bit different. When we did it for the quadratic formula, we solved for x. We let f of x be 0. Okay. I'm gonna let f of x stay f of x, and my goal here is actually go through the completing the square process just like we did with the quadratic formula. But instead of solving for x, I want to try to solve for f of x again. Okay? Because it should give me something different. Completing the square now. We took half of this, right? Half of this, so that would be b over 2a, correct? And then we squared it, correct? So take b over 2a, and you square that. Doesn't it turn into b squared over 4a squared? That make sense? Okay. Can I add that to this side? B squared over 4a squared. Okay. We cool? All right. The reason we do that is because that now is a perfect trinomial. It becomes x plus. It was half of this term, right? Half of that term. What's half of b over a? B over 2a squared is now equal to b squared 4a squared plus f of x over a minus c over a. What kind of multiply everything by to make things maybe a little bit? What kind of multiply to get rid of these a's right here? A. Multiply everything by a. Now it doesn't really help with this first fraction, but it gives me b over 4a. Okay? This is going to be f of x. And this is going to be minus c, right? It's going to be a, x plus b over 2a squared. And the reason I did that is because I want to be able to solve for f of x here. So I'm going to, would you agree that this thing here can get moved to the other side? And so can that? They're just numbers.
Why does it not be square on top of it?
It should be, sorry. So now I'm going to move that to the other side, so it's going to be a as x plus b over 2a squared. Okay, so now this is going to be, we can go plus c, and then we had to subtract b squared over 4a. And now the order that you, write this, that's stupid. There should be a highlighter. All right. The order that you write that is obviously commutative, right? You can flip that as negative b squared plus, or over 4a plus c. But let's look at that. Okay? We now just took ax squared plus bx plus c, which was in polynomial form. And then we put it in the vertex form? Yeah. If we understand transformations, that means when I have my traditional x squared where that is 0, 0, that vertex is 0, 0, doesn't that make it go left or right, b over 2a units?
Yeah.
That make sense? Okay. And it's going to be the opposite direction of whatever that number is, correct? If that's a positive 3, it moves it left. If that's a negative 3, it moves it right. So our x-coordinate of our vertex is going to be the opposite of that number. Opposite of b over 2a. Does that make sense to everybody? Okay. What I'm trying to show you is that Algebra 2 last year, you were told this fact. The x-coordinate of your vertex is opposite of b over 2a. What I'm trying to show you is that you were told that was a fact because of this process of completing a square, which we can do with these specific problems, okay, with specific coefficients. If we do it with generic coefficients, we actually generate the formula. Okay? So what is this then? Isn't that the y-coordinate? Isn't this everything? Think about it this way. Isn't this a x plus h squared, sorry, x minus h? X minus h squared plus k. Doesn't this thing here match up to b over 2a? So isn't the opposite of h equal to b over 2a? Does that make sense? So doesn't h equal the opposite of b over 2a? That thing then has to be k, right? Which is our y-coordinate of our vertex. Okay? Now, in any Algebra 2 textbook, any college algebra textbook, any textbook, you will never see c minus b squared over 4a as your y-coordinate. They're never going to give you that. You can use it if you want to. Okay? Think about this. If I go back up to this thing right here, okay? If I take the opposite of b over a, opposite of b over a, or b over 2a, sorry. So I get negative 24. Take the opposite of that, gives me 24, right? Divided by 2a. Well, that's negative 6. Gives me negative 4. The x-coordinate is negative 4. Now I'm going to find my y-coordinate. Well, my y-coordinate said it was c. So c in this case is negative 46 minus b squared. Well, b squared is negative 24. So I'm going to square it. I don't really care that it's negative. So b squared over, what's 4a? So 4 times negative 3, let's write negative 12, be easier. And my y value of 2? Make sense? Okay, so now I know that a is going to be x plus 4 squared plus 2, and that's much quicker, I think, than going through the completing the square process, right? So when we told x equals the opposite of b over 2a, it's completing the square. That's where we get that. That's why that works, okay? So does that allow me to circumvent completing the square? Does that mean when you get to your homework, do you have to complete the square? No, okay? Now, if you think about what the c minus b squared over 4a is, it is actually the same thing as taking my g function. If I evaluate it at the x-coordinate, negative 4, it would be negative 3, negative 4 squared, minus 24 times negative 4, minus 46. What's negative 4 squared? 16 times 3, we get negative 48. That's 96 minus 46. Okay? Negative 48 minus 46 is negative 94. What's negative 94 plus 96? 2. Is that the same thing as your y value? Okay? So that's why in textbooks you'll never see that k value written that way, because their argument is, and I would agree with this, hopefully you do too, is that if I have to remember b over 2a as my x-coordinate, obviously b over 2a as my x-coordinate, and my y-coordinate is c minus b squared over 4a, that's a lot to remember formula-wise. But if I just remember the opposite of b over 2a gives me my x-coordinate, and if I evaluate my function at that value, it gives me my y-coordinate. The argument is that the process of remembering the opposite of b over 2a in substitution is easier and more effective and less confusing than remembering both those formulas. Does that make sense? Okay. So, find opposite of b over 2a, substitute it in. That's going to give you your k value, okay, your y-coordinate of your vertex, and then you can kind of move on as you need. Now, as I did that, that gives me just this, right? Okay. Use exactly what Blaise said. Well, isn't the a value here going to be the same as the a value down there? Has to be. Has to be, because if I FOIL that out, it doesn't give me x squared plus 8x plus 16 and an a and then plus a 2, right? So the only way that I can make this work is if I multiply that a through 8ax plus 16A plus 2. The only way that I can get that number right there to match up to that number right there and these things to kind of combine to those two numbers is if the A is -3. Does that kind of make sense to us? Okay. So, what we're going to see as we move through this course is, Chapter 1 and Chapter 2 kind of defined collectively relationships or concepts that are going to exist in other specific functions. So meaning, when we looked in Chapter 2, we were just looking at all kinds of different curves, right? Okay? And we talked about maximums and minimums. Well, now we're going to come back to just a quadratic and talk about the maximum minimum. Okay? If we have it in vertex form, and it doesn't really matter if it's in vertex form, we determine the same logic in polynomial form. If your A value is positive, it's bigger than 0, that's what this is saying. If A is positive, concave up, right? Then you have a minimum. And once you know your minimum, based off of your vertex form, you now know that to the left of that minimum, your graph is doing what in terms of your Y values?
Increasing.
To the left of your minimum, your Y values are, because you read it left to right. So I'm going to put my cursor right here. And as I move to my minimum, what are my Y's doing? Decreasing. Okay? To the right of my minimum, my graph is increasing, right? So those are things that we can determine once you take you don't even have to graph it. Once you take your polynomial, let's say we have absolutely no idea what I started with, but let's say that I end up with, let's say -3 x plus 5 squared minus 4. Okay? That tells me my vertex is located at what x value? -5. This tells me this is concave what? Down. So that must mean at this point, -5, -4 is a maximum. Good. Okay? If it's a maximum, that means then to the left, so -infinity to -5, to the left of that x value, you are increasing. Does that make sense? To the right of that maximum, -5 to infinity, you're decreasing. And I can gain that information, guys, without ever having to look at the graph. Does that make sense? Now, I might have, that idea that I drew that. That might be in my mind, okay? But I didn't have to have a specific graph to determine that information. Why is that important? Because there's a spot, and it's at x equals -5, that increasing changes to decreasing, okay? Obviously, that's our vertex, that's our maximum. Calculus-wise, that becomes very important to us. Okay, I'll kind of show you. We're going to have time last class to do another example. So I'll show you kind of where this is leading to in calculus. Okay, understand I keep talking about calculus. You don't hear me talk about stats class or linear algebra or anything like that because college algebra is designed to get you ready to take calculus. Does that make sense to everybody?
Yeah.
Okay. So that's why I always want to kind of talk about calculus to get you thinking about that. Okay, there are other pathways you can take. This course is kind of that algebra that's going to bridge the gap between what we know and what we need to know to get to calculus. Okay. If A is negative, that's a maximum. Okay, and then we know to the left of that maximum we are increasing, and to the right of that maximum we're decreasing. Okay. So let's just kind of look at this one real quick. And say, okay, what is the vertex? Okay, let's put this in vertex form. Well, I'm going to go for vertex form. Let's just see if we can hash this out as fast as possible. That's the goal, right? To be efficient. So what is my x coordinate for my vertex form? How do I find that? -b, opposite of 30, over 2a, so 10, so it should give me -3, right? Okay? So so my x-coordinate is going to have a -3. Does that make sense? Now, just be careful. When you plug that in here, your h is -3, right? So does this turn into +3? Okay. Now, my k value is this function evaluated at -3, right? If I plug -3 in here, okay, so it's going to be 5 times 9 minus, 120? It would be plus 120, plus 49. Is that okay? So that's 45. So, 165? Huh? Yeah, I'm not very good at math. Thanks, Chuck.
There you go, Chuck.
So this was what? 45? This was plus 90, and then plus 49. What's that turn into? 184. Okay. And now, what does that number there have to be? It has to be 5. Okay. So 5, x plus 3 squared plus 184. Okay. We know that the vertex is at -3, 184. Okay. -3, 184. That's positive. So this thing is concave up, right? So from -infinity up to -3, this thing is increasing. From -3 to positive infinity, decreasing. So that's -3 right there, right? And the x-coordinate. So from the left to that point, okay, so from -infinity up to -3, you're decreasing. And from -3 to infinity, you're increasing. And that's all information that we hope to gain from just being able to know what the vertex is. Okay? So I said I would talk about where this stuff leads us in calculus. Our goal in calculus, guys, is to, one of our goals is to kind of analyze the slope of the tangent line to this curve. You guys remember talking about that the other day? It was actually about 2 weeks ago. I gave you this formula, f of, I would call it like x plus h minus f of x all over h. Remember that? Okay, that's called the difference quotient. And we talked about that being slope. That's a formula that provides a slope. Okay. Well, slope on a parabola changes. So what we're thinking about here, guys, is that if I take maybe that line right there, terrible. Zoom in a little bit. The idea is if I take any point on here, so that point there, and I want to find the slope of the parabola at that point, it's the same as the slope of that tangent line right there. If I find that slope of that tangent line, it's going to tell me the same slope of that curve. Well, if I want to go to that point, now that tangent line is that line. Does it make sense? Is it a different slope? That's a positive slope. Would you guys agree with that? What about a slope over here? What's that slope going to be? Negative. If I go from positive to negative in anything on the number line, what is a value that I know I had to pass through? If you transition from positive to negative, you pass through 0. Where is the slope 0 here? At the vertex. Okay. If I draw a tangent line in there, it's that horizontal line. It's the slope of 0, right? So let's take this thing here and see if we can generate that idea. Okay. Now we did. Try to find my formula. Where did that thing go? I forget what it was. Was it negative? F of x was negative 3x squared minus 24x minus 46. What we did back in like section 2.5 with the average rate of change, okay, is that we were trying to actually set us up to find what we call the derivative, which is just a formula that tells me the slope of those tangent lines no matter where on that parabola. Okay. What you're going to find out next year is that process is a long process, and there's some shortcuts. Okay. One of those shortcuts is what we call the power rule. And the power rule in calculus says take that number right there
multiply it by that number out there. So what's negative 3 times 2? Negative 6. Okay? And you're going to write your variables down there. And now you're going to subtract 1 from that exponent, or from that power. What's 2 minus 1? 1. Okay? So I just found the derivative. You just found the derivative of what we call negative 3x squared. Okay? So that is, negative 6x is actually a formula that tells me the slope of any line on the parabola of negative 3x squared, or any tangent line on the parabola of negative 3x squared. Let's go through the negative 24x. Okay? Power there is 1. Take that 1 times the negative 24. What's that give you? Negative 24. Subtract 1 from that exponent gives you x to the 0. What's x to the 0? Just 1. So negative 24 times 1, right? Do the same thing here. That's x to the 0. What's 0 times 46? 0. Does it matter then what my variable is? No. 0 times anything is 0. So I just get f of x is equal to negative 6x minus 24. Now we call that f prime. That's the notation to talk about a derivative. Okay? You guys remember doing that process where we canceled the h's and stuff?
Yeah.
2-3 weeks ago?
Yeah.
Okay? That is what's generated when you would do that. Okay? If I would evaluate this as x plus h, multiply that x plus h through as x squared and the x in the negative 24, that kind of stuff, and cancel all the h's out, I get negative 6x minus 24. Why is that useful? When does, you said the slope, because this gives me the slope, this gives me the equation of the slope of any point on that parabola. Well, you said right here at the vertex, the slope had to be what?
0.
0. This says the slope of tangent lines, I'm going to say 0, is negative 6x minus 24. If I solve for x, I get 24 equals negative 6x, right? What's x give me? Negative 4. What was the x coordinate of your vertex? Negative 4. Okay. Now, why is that useful? Because when we get to graphs like this, okay, in calculus, we're going to address that graph right there tomorrow, but we don't have the ability to find the max and mins in that graph right there. It's not until we use the calculus to do that.
Are you assigning more homework?
The current homework is due tomorrow.